Hello everyone. Today we are going to discuss about X-rays. So, what do you know about X-rays? X-rays are the part of electromagnetic spectrum which falls under higher frequency range, or we can consider it to be shorter wavelength range. So, if you remember the electromagnetic spectrum, which is given by Gx mu v Gx mu v is equal to infrared, microwave, radio wave. Isn't it true? So this is the electromagnetic spectrum, and in this electromagnetic spectrum, these we can say that this goes is increasing wavelength, or we can say decreasing frequency. Okay, so in this electromagnetic spectrum, this X is the X-rays, and the typical range of X-rays is 10 to the power minus 8 meter to 10 to the power minus 11 meter. Sometimes written is 10 to the power minus 12 meter, but this 10 to the power 12 and power 11 range is the overlap in between X-rays and gamma rays. Okay, so what are the things that we should know about X-rays? X-rays has high penetrating power because they have higher frequency. X-rays can be considered or can be categorized into two parts: hard X-rays and soft X-rays. Soft X-rays means those X-rays um, which has yeah wavelength of 10 to the power, which we can say that soft ray are the X-rays for which the range of wavelength lies in between 10 to the power minus 8 and 10 to the power minus 10. Similarly, hard X-rays are those X-rays for which the wavelength range lies in between 10 to the power minus 10 to 10 to the power minus 11 or 12. Okay, now 11 and 12 is a very overlapped thing in between X-ray and gamma rays, so we can't always be exact where there are hard X-rays. How do we, or we can say, how do we uh, define X-rays in this reason? Okay, so these are some of the things that you should know about X-rays. X-rays were first discovered by Wilhelm Röntgen, and so these are the things you should know about it. And one of the things that you should know about X-rays is that the soft X-rays are frequently available, are massively available in our atmosphere, and they interact with us, but they don't have that much of penetrating power to penetrate us. That's why all the X-rays that you see in the case of medical equipments are all hard X-rays. Okay, that means those X-rays which has their wavelengths larger, no, not larger, but smaller than 10 to the power minus 10. Okay, so these are the actual used X-rays in the case of medical field. So these are some of the things you should know about it. And X-rays can be formed by Coolidge tube. Uh, I hope I am pronouncing it right. Coolidge tube. Okay, this can be formed or produced by using Coolidge tube. And in this Coolidge tube, what we do is, okay, I think I should draw that Coolidge tube and explain how we produce X-rays. Yes, this is the Coolidge tube, and I am going, actually, I am going to make you, yes, so I am going to make a promise to you that when I explain all of these X-ray formation process, you would be surprised that how beautiful this phenomenon is, how amazing this phenomenon is. Okay, so let's directly go into it. So this is something called Coolidge tube. So where should I write the name? Let's write it here. Oh, okay, but Coolidge tube. This tube here is called experimental apparatus. It's called Coolidge tube. And if you see in this Coolidge tube, you have to see two to three things. First one, there is a cathode, and the cathode and the filament act as a cathode. There is a tungsten, and tungsten act as anode. We have some high tension voltage supply there, and we have some rheostat and battery voltages there to regulate the speed of the electrons that are produced in this cathode. Okay, so actually not the speed but the number of electrons so actually what happens is this filament is being heated by this rheostat and this voltage supply. When we increase this voltage supply and decrease this resistance, the filament would heat more intensely, and as a result, the more number of electrons will be emitted by this filament. Okay, so this is the apparatus. Now let's understand the phenomenon, and then we will go why would happen. What is the theory? Theory is beautiful. So let's understand the phenomenon. What happens is whenever we have such kind of Coolidge tube, and you heat this filament, then electrons would be formed. Electrons would be produced at this cathode, and these electrons, the speed of electrons is managed by this high tension voltage, and at appropriate value of this high tension voltage, maybe let's suppose nearly 10 to the power 5 volt, the electron would go or rush towards the tungsten and hit the tungsten. Now what happens after hitting the tungsten is interesting. At this point, somehow photons are emitted which has the wavelength equal to that of the X-rays. That is 10 to the power minus 10, 10 to the power minus, actually 10 to the power minus 8 to 10 to the power minus 11. So this range, the photons that are emitted in this process are in this range of wavelength. This is the thing. This is the phenomenon that happens. Now let's understand why this happens. So it turns out there are two mechanisms. Okay, there are two mechanisms for production of X-rays here. One is called breaking radiation. Another one is called characteristic X-rays, or we can say that first there are two kinds of X-rays that we will see being produced in this Coolidge tube. First one is the characteristic X-rays. Second one you can say to be continuous X-rays or Bremsstrahlung, also known as breaking radiation. Okay, so now there is the phenomenon of the theory of phenomenon, how those two kind of X-rays are formed is completely different. Let's go to the theory of how the continuous X-rays, the Bremsstrahlung or breaking radiation is formed. So it says the theory predicts that let's suppose we have tungsten. We have a tungsten, and inside tungsten we have a large nucleus, and these are the electrons that are formed and that are moving towards the tungsten. So theory predicts that whenever we have such condition, electrons that goes towards the tungsten schemes or zooms nearly, very near, or maybe now the distance may differ, but whenever these electrons move and comes near the vicinity of the nucleus, due to the electrostatic repulsion or attraction, due to the electromagnetic attraction in between electron and nucleus, the speed, the velocity of the electrons decreases. Okay, the velocity of the electron decreases and it abruptly changes its direction. The electron abruptly changes its direction due to the electrostatic attraction in between nucleus and electron. Okay, and because of that abrupt change in the velocity, now this due to the change in the due to the abrupt decrease in the velocity, our energy, the energy of the electron would also decrease, also change. So this change in energy is given by h nu. Now it turns out at that particular scenario, this change in energy is manifested by the releasing of photons, and those photons that are produced in this scenario have the wavelength of X-rays, that is 10 to the power minus 8 meter to 10 to the power minus 11 meter. So this process is called the formation of continuous X-rays, or formation of Bremsstrahlung, or formation of breaking radiation. Those three names essentially mean the same, continuous X-rays. So this is now, it depends upon the loss of energy, or the intensity, not the intensity but the frequency of the X-rays, or the energy of the X-rays depend upon how close the nucleus and the electrons were during that electromagnetic attraction, how abrupt the change is to the direction of the electron. The higher the abrupt, or we can say more abrupt the distortion is, the more intense the X-rays are. Okay, and by intensity I mean the energy of the X-rays, I mean the frequency of the X-rays. Okay, so this is what is one of the process to produce X-rays. Now another X-rays are, or other type of X-rays are formed in a more interesting way. Those type of X-rays that I'm talking about right now, now I'm going to talk about right now, is called characteristic X-rays, and these are not very frequent, but these really happens. Okay, so these really happens, but these are not so frequent as in the case of Bremsstrahlung. So characteristic X-rays are formed in a very unique way. Let's suppose we have tungsten and a lot of electrons are there. I am considering this to be atom. Okay, so let's suppose maybe yeah, let's suppose electrons came from the tungsten, no, not the tungsten but the filament, and it turns out that filament is also made up of tungsten, so I am not that wrong, okay, to say that it to be tungsten. But let's suppose this to be tungsten atom, and let's say this to be a filament for more clarity. So let's suppose electron moves towards the tungsten atom, and what happens in the case of characteristic X-ray is that this electron is so intense, has so much of energy, is so fast that is that it goes and knock electron. And which electron? Not the valence one, but the inner shell one. So what it does is it knocks this electron to the higher energy or higher energy orbit. I think you should see it more clearly. Sorry. Yeah. So this inner shell electron is knocked off by this electron to the higher shell or high energy shell. Now we already know that this electron is in a very unstable position. So it has to lose this energy somehow by releasing it as a photon. So what it does is it does the same thing, exact thing, and it releases this energy in form of photon. Now it turns out that this frequency lies in the range of X-rays, and these are really very intense. So these mostly lie in the hard X-ray region. Okay, so this is another process which is called the characteristic X-ray formation, and this is the phenomenon how it does form the characteristic X-rays. Okay, and if you see X-ray spectrum, you would see a graph which looks like this. You would see a graph of the X-ray spectrum which looks like this. If this is the X-ray spectrum, you would see some spikes. Okay, now these spikes represent the characteristic X-rays, and these smooth curve represents continuous X-rays or Bremsstrahlung. Okay, so this is what you should know about X-ray and X-ray spectrum. Okay, let's talk about fine structures of X-rays. Now there are some of things that you should know about fine structures of X-rays, and even before that, yes, and even before that, you should know about the reason for the fine structures. And we have already exclusively talked about fine structures for 36 minutes in the previous video, so I don't think I should repeat it. But let's just see. Let me just say the definition of that fine structure of fine structures. Fine structures is a phenomenon where a single spectral line is split into two or even more of the spectrums, and this is a result of the LS coupling, the orbital angular momentum coupling, the orbital angular momentum and the spin angular momentum coupling in between them, or the interaction of the spin and spin orbit interaction. Fine structure happens. Okay, now you must be wondering that how the hell did fine structure even came here. Okay, we are talking about X-rays, we are not talking about emission or any kind of other emission and absorption. So how does this come here? Now if you remember, we have just studied a case where absorption happened and emission also happened, and that was the case of characteristic X-rays. That means in case of X-rays, the fine structures, the concept of fine structures come into the scene because of the characteristic X-rays. Because if you see in the characteristic X-rays, an electron, because of the energy provided by another electron, jumps into the higher energy state. It is just absorption. But after some time, that electron in the higher energy orbit would try to get down into its own original ground state, and during that a spectral line would form. And it turns out, since it's an electron and it has its spin orbital moments, that means it would split and form not only two but many. It can be many. So it would split into many of the spectra, or yes, spectra, and that is what we are accounting in the case of fine structures of X-rays. So the thing that you should notice, and the thing that you should never forget, is that fine structures of X-rays only comes into scene when we talk about characteristic X-rays, okay, not in the case of Bremsstrahlung. Now let's suppose our electron, uh, okay, let me create the scene here. Okay, let's understand fine structure. Now before going to this fine structure, I want to make clear some of the things. Now there are two ways to represent these spectral lines. Now someone, okay, I think I should write it with some another color. Yeah, always remember that, okay? Always remember this, what I'm going to tell you. So, come on, these people. Yes, so there are two ways to represent the spectral lines. First one is 2s plus 1, 2s plus 1 and something maybe x. This is a denotation, this is a notation, this is a notation, this is a first type of notation. Second type of notation is nx nxj. This is another type of notation. So what are these notations for? These notations are for the spectral lines. Whenever you want to represent a spectral line from some level to some level, this type of notation, what you do is, let's suppose you want to go from n equals 2 to n equals 1. Then according to this notation, you would write something like this. 2x, maybe something j, n equals 2 means n minus 1 is 1. 1 means 1 plus half. So you would have 3 by 2 or 2x 1 by 2. Now since n equals 2, that means p. Now this x here belongs to S, P, D or F according to the value of L equals 0, 1, 2, 3. If 0, then it becomes S. If 1, it becomes P. If 2, it becomes D and so on. Okay. So if you use this notation, you would write these spectral line is this. Okay. Not P but rather S. In this way. So you would have two spectral lines. First one from this to this, second one from this to this. Alright. But if you use this kind of notation, then here S represents the spin of electron, and spin of electron is always 1 by 2. So this quantity is always 2 per electron. So in the case of, if you use this type of notation, our spectral line would be same here but different here. This is always, the ground is always duplet in the case of this notation. So always remember that. Now people use different kind of notations for spectral lines. Okay, our book may use something else. So I am going to do something else. So you don't have to be worried about it. You just pick up one of the way of writing the spectral lines, you can just use it forever. Okay, so this is what you should be careful about. So now let's go directly to this X-ray spectrum. Sorry, find the structure of X-ray. So let's suppose we have an electron which draw from K shell to L shell to K shell. Okay, whenever we say L shell, that means value of L equals 1 and value of principal quantum number is 2. Similarly, when I say K equals shell, K shell, that means L equals 0 and N equals 1. The transition from L shell to K shell is given by K alpha. This is the notation. Alpha here account for the fact that the spectral line comes from n equals 2 to n equals 1. Actually, it's n equals 3 to n equals 1, n equals 2 to n equals 1. Okay? Well, if it has came from n equals 3 to n equals 1, it would be called as beta. Okay? Now, in our case, since electron is dropping from L cell to the K cell, L cell to the K cell, this K alpha line is the spectrum of interest, the spectral line of interest. Now, it turns out due to the spin orbit coupling, this K alpha splits into two spectral lines given by K alpha 1 and K alpha 2. So this is the overall concept of this is the overall concept of fine structures in the case of X-rays. Now, one thing you should remember is that if you remember the previous case of formation of characteristic X-rays, we had tungsten. Okay, we had tungsten, and we know that tungsten has large number of electrons. Large number of electrons. So whenever we have that number, actually, I think the atomic number of tungsten is 74. That means we have 74 electrons, and we can't just write or form a characteristic or diagram, of energy diagram or spectral diagram for an atom which has 74 electrons. That is literally impossible for for a limited period of time. So that's why we don't draw the whole thing that is given in our book. We just write the concept, why X-ray, why fine structure happen, when happens, that means in the case of characteristic X-rays, and how do we show it for the small cases, like from the like for the electron which comes from L cell to K shell. Okay, you don't have to worry much about it. So this is it, all about uh, fine structures of X-rays. Now, to talk about the uses of X-rays, X-rays has unlimited. I can't even finish or I can't even stop and how can I say it? If I sit and if I start talking about the importance of X-rays, it won't get finished until I get finished. Okay, that means it has so much of the importance. One of the importance that we might want to know, and if I say this importance, you would be amazed that in case of black bodies or black holes, the data captured by the telescope from the cosmos about the black holes, we do X-ray analysis of that data collected by the telescope and find out the energy, where that black hole is, okay, where that neutron star is in the cosmos. So that means the X-rays collected by telescope And the analysis of X-rays help us to know about the temperature, where it temperature of the black hole, where the black hole lies, and a lot of other things. So this is only one aspect of the importance of X-rays. So you don't have to talk about and you don't have to worry about where where I will use this knowledge. Okay, trust me, you would use it in so many places that I can't even talk about right now. Okay, so this is for importance of X-rays, and there is something called XPEC, and we use that for X-ray analysis for the data collected by the telescopes. Now, one of the telescope that is explicitly used for X-ray collection or X-ray detection in the cosmos is Chandra X-ray Observatory. Okay, and so these are some of the things out of the syllabus that I wanted to talk. Now let's get back into the topic, into the syllabus, and let's talk about something else. And the something else is Moseley's law. Now it turns out that the periodic table, the, the periodicity in the table was also understood by X-ray analysis. Now let's see how. Okay. So Moseley's law. The frequency of X-ray lines varies in a regular manner with atomic number Z of the target atom. That is, root under of the frequency of the X-ray spectra or any line of the X-ray spectra is directly proportional to the atomic number of the metal in which that characteristic X-ray was formed. Now this is true for any spectra, not only for the K. I have drawn the K. What I have drawn here is the relationship in between this and this, and it turns out to be a linear relation. And this linear relation is true for not only just K spectra, but L alpha or M alpha, whichever is feasible by the spectral rules, no, not spectral rules, but the selection rules, whichever lines are possible using the selection rule, these always have the linear relation in between root under nu and z. So this is Moseley's law. Now it is not a very interesting relation because it was already found out by Bohr. I'll show you how. Now Bohr had already found out the relation which looks like what is it? Frequency is equals to G square RC times R is the Rydberg constant 1 by n1 square minus 1 by n2 squared, and from this it is okay. Now this formula is what Moseley is talking about. Now if we consider n equals the transition which formed the X-ray to be from K shell, from L cell to K cell, that is from n equals 2 to n equals 1, then mu would be this value. If we keep account of the screening effect, you know screening effect, right? Shielding effect, then that is given by shielding effect means when we have inner electrons, then these inner electrons would have much stronger bond, so that's why electron from this near the nucleus, electrons from the cells near the nucleus would be much attracted or would be attracted towards the nucleus with much greater force than this one. So whenever we have some impact from here, the first thing that's going to bear that impact are the outer cells, not the inner cells. So this is what called as a screening effect or shielding effect. So to keep that into account, we introduce a term called B, and if we do that, we would get d squared minus b, sorry, not b, but g minus b squared, and that, if I consider this to be a, this is what Moseley's law is. Okay, this is what Moseley derived. So this is not what is important here. Actually, the importance here is the interpretation of this theory. Interpretation of this relation given by Moseley is this. So what is the interpretation is? What the interpretation is? The interpretation of this is that well, okay, what is the interpretation? Interpretation is that the relationship between the frequency of the spectra and the atomic number of the atom where that X-ray transition happens is linear. The relation is linear. That means as the root of frequency changes, as the frequency changes, increases, the atomic number also increases. As the frequency decreases, atomic number also decreases. So this is what it essentially means. Now let's try to understand the importance of it. Okay, let's try to understand the importance of Moseley's law. Prior to this uh, theoretical explanation of Moseley, people used to use Mendeleev's periodic table. Mendeleev's periodic table was something or where the electrons, not electrons, but elements were arranged in terms of atomic mass. Okay, that means people prior to this theory or this law used to think that the atomic mass is the one which remains regular at the regular intervals, which remain periodic, but that is wrong. After this, people found out that uh, the periodic thing here is atomic number, not the atomic mass. So the physical as well as wait a second. To say it in better way, it says that according to this law, the atomic number, not the atomic weight, of the element determines its both physical as well as chemical properties. Therefore, atoms must be arranged in a periodic table according to the atomic number, not on the basis of atomic mass. This would remove some discrepancies in the order of the certain elements in the Mendeleev's periodic table. Okay. Now, another importance of another importance of this uh, Moseley's law is that this law has led to the discovery of new elements like technetium, promethium, hafnium, rhenium, Ricci by the indication of the gaps in the Moseley's diagram. This law also helps to determine the atomic number of rare earth elements and fixing their positions in the periodic table. So, X-rays and X-ray theory and the simple law, this simple looking law used or revolutionized our periodic table entirely, so much so that we are using the same periodic table even after 100 years. That is massive progress. Come on, these. Okay, another important theory is about the absorption of X-rays. So, if you see the absorption of X-rays, we can consider this scenario. Let's suppose we have X-rays and these are incident on this matter. Matter can be anything, water, solid, or even gas. No, if I consider gas, then it would ionize it. So a lot of other things would come into play. That's why just for the simplicity, let's just imagine this to be a solid matter. Okay, so let's suppose this to be a solid matter. Then this will obviously the X-rays has large penetrating power, so they will penetrate this and goes to the another side. And after that, the quantities I intensity, F frequency, and lambda are calculated. And it turns out that even though the frequency and lambda remain same as it is in the previous case, it turns out that the intensity of the X-rays decreases. That means some of the X-rays, even though how much powerful it is absorbed by this matter. Obviously, this won't be the technical diagram for our experiment. So our experimental evidence, or sorry, not evidence, but experimental apparatus looks like this. So we would have a X-ray source, which I used as a college tube. I used college tube for the source of X-rays, and after that, I put a slit so that I could get a monochromatic beam of X-ray. I get a monochromatic beam of X-ray, and I pass that X-ray through an absorber or any matter, and after that, the transmitted X-ray is passed into an ionization chamber, and I calculated the ionization current. It turns out that the intensity decreases. Okay, now for the reason why this intensity decreases, and for the theoretical part, let's see the derivation. Okay, let's talk about the theory and the derivation. So this is the theory. Let's suppose we have I naught to be the incident intensity, I to be the transmitted intensity, di to be change in the intensity. Then experimentally it was found that if we consider a case of linear absorber, linear absorber, okay, of thickness x, in that case the change in intensity depends upon two factors. Two things. First one is the transmitted intensity. Second one is the thickness or the change in thickness. That means the decrease in the intensity. Wait a second. Yeah, this is what. Wait a second. Yeah. So it was found that the di is directly proportional to I and di is directly proportional to dx. So if we combine this, we would get di is directly proportional to I times dx. If we introduce a proportionality constant, I introduced minus mu, because minus mu is called, sorry, mu is called the linear absorption coefficient. Okay, mu is called linear absorption coefficient, and minus is introduced here because the if the uh, thickness of the material increases, then the intensity decreases. That's why a minus sign is needed here. Now, if I integrate it, I would get log of I this, and let's uh, suppose at x equals 0, I equals I naught. If that is the case, our C would be log of I naught. Similarly, after some calculations, I would get this equation, I equals I naught e to the power minus mu x. Now the intensity decreases as the thickness increases is the interpretation of this formula, because you can see it's an exponential function, and in the exponential we have a minus sign. That means it would exponentially decay. The intensity would exponentially decay as a factor of x. Okay, so if you want to plot x and intensity, will exponentially decay. That means whenever we increase the thickness of the material, of a linear material, that means the intensity would decrease. exponentially. So after this, we can do some modifications to this formula, and the modification involved, I think you could see this, right? If you can't, let me just decrease the brightness. Can you see it now? So I hope you are seeing it. So what I did here is, now in this formula we have mu x, right, minus mu x. So I introduced a rho which account for density in both numerator and denominator. Now we know that this component mu x becomes mu, sorry, not mu, but what is it called, rho. Rho x equals mass, and minus mu by rho is called is mu m, and this mu m has its name. It is mass absorption coefficient. Okay, it's mass absorption coefficient, and this mass absorption coefficient has a relation with atomic number, and the relation looks like this: mu m equals k times of lambda to the power 3 and z to the power lambda, g to the power 3. That means whenever we have larger g, that means whenever atomic number is greater, mu m is greater. That means mass absorption coefficient is greater. And whenever that means whenever we have, so if I substitute this here, I would get k lambda cube g to the power 3. It says that when the z increases, when the z increases, when the z increases, eventually the mu m increases, and as a result of this exponential decay, this intensity would decrease. That means whenever we have an observer with higher atomic number, in that case our intensity would decrease much. Okay, so this is all about it. This is all about it. Now so this is it about the absorption of X-rays. Okay, one thing that I forget to mention here is that if you remember, whenever we pass high intensity X-rays through a matter, it just does not only pass through it, but it does something else. I want to ask you what it does. If you remember, this is the, okay, yeah, wait a minute, okay. Yes, so we were talking about mu, and I forgot to mention that we have a lot of other things that going on here. Okay, so mu here is a linear absorption coefficient which is dependent on the wavelength of X-ray and the nature of absorbing material. It is just a fact, and I have just written this for the account of that fact. But another thing that here, oh wait, what I was explaining here is, I was explaining this thing, right? So I was asking a question that if we apply a X-ray to a material, the matter absorb the X-ray, and it would transmit some of the X-rays, right? So one of the thing that you should notice here is that this is the exact same thing can happen. Wait, okay. So what I should say is that these X-rays here have energy. So sometimes when they are passing through a material or absorbing through when they are being absorbed by a material, transmitting from that material, if the electrons, sorry, yes, if the X-rays have enough energy, then they can knock those electrons out from different cells, and as a result, characteristic X-rays could be found in such a way that the characteristic X-rays that are found now would have lesser frequency but longer wavelength. Okay, so it means that by the help of the absorption of X-ray during the absorption of X-ray, we can form we can form uh, the characteristic X-rays even from the normal X-ray, that is the Bremsstrahlung. So that means Bremsstrahlung can also form characteristic X-rays during absorption. And this particular phenomenon is called X-ray fluorescence. Okay. Now we have to understand also, a little bit of something here, and that is X-ray absorption edges. X-ray absorption edges given by this something else. So what does this mean? So we are talking about, yes. So let's understand this. So we are trying here to keep account of mu or the changes of mu with respect to lambda. Now, if you see a formula, it looks like this. Mu is directly proportional to the lambda cube. But if you want to see it through the phenomena, this is what really going on here. Let's assume this kind of scenario. Let's suppose we have an atom. Okay, an atom, and let's suppose Z is greater, because if so we have already said that when we use the what is it called, Coolidge tube, yeah. So Coolidge tube, then we would have to use atom of large atomic number for the X-rays, right, for production of X-rays, right. So that's why let's suppose that atom is of Z is greater. Okay, that means atom is of uh, higher atomic number. So if that is the case, then let's suppose that these are the X-rays, these are the incident X-rays. Okay, these are the incident X-rays. This is the climax. Okay, this is the climax of the lecture. So this is the uh, X-rays that are introduced here, that are incident here. So yes, X-rays are incident on this atom, and let's suppose we are at here at the origin, and we are trying to draw this graph. Okay, so it turns out that if we increase the mu, that means mu. Now, what does mu means? Mu means is a linear absorption coefficient. That means how much of the intensity is being lost from the original intensity. So when we increase in this axis, when mu increases, that means the intensity is decreasing. Intensity of the X-rays are decreasing. And whenever we go here, when we travel through this axis, y-axis, that means our frequency is decreasing. That means our energy that the X-rays have decreases. So whenever both of these alternate, or how can I say it, rivalous, okay, I'm going to use the term rivalous. I don't know even that exist or not, but let's suppose these two rival quantities, not these two quantities, but the, both of these quantities are rival to the energy of the X-ray. So when these increases, the energy decreases. Okay, if that is the case, the X-ray are being continuously flown through this particular atom. So whenever we have lambda greater, that means whenever we are near to the origin, the X-ray would knock these inner shell electrons, and as a result, we would get characteristic X-rays. And at that particular point, we see a drop. Similarly, when the lambda further increases, we would see further decrease in the frequency, that means further decrease in the energy of the X-rays. And when the energy of the X-rays decreases, it would target the outer shell electrons, not the inner shell electrons, when the energy decreases of the energy of the X-ray decreases, the shielding effect would be more heavier, more dominant than the X-rays. That's why the X-rays can't even pass towards the inner electrons. That means the X-rays will now target the outer electrons, and that outer electrons would knock. So that means the X-ray would knock some other electrons from outer shell. Okay. Similarly, at the peak of the at some point of lambda, at the peak of mu, the X-ray energy becomes so small that it target the outermost electron. That means it would target the outermost electron and it ionizes it. So it would ionize it, and because of that, we would get a sudden drop here. So now what does these drops mean? These drops mean the X-rays or some of the electrons have been knocked out from this atom at this particular value of lambda. Now this value lambda can be calculated for different kind of atoms. I'm not going to ask that, but as a phenomena, this is what happens, and this kind of phenomena can be captured by X-ray absorption agent when we draw the quantities mu and lambda into axes. Okay, I hope this was a good explanation for the X-ray absorption. So okay. Last thing that I want to say is that now, as you know, that these absorptions, these absorption, not absorption but emission of X-rays. First one is called K alpha, then L alpha, similarly M alpha, and so on. That means what it means is that first when the X-rays had larger energy, has huge amount of energy and huge number of energy and smaller amount smaller lambda, then at that condition the emission was from the inner shell, that is from n1 equals 1, or let's suppose n2 equals 1, n2 equals 2 to n. But when the lambda decreases, so lambda increases and energy decreases, then the emission started happening from the larger atoms. So not larger, but this larger principal quantum number. So we got this emission here, and that can be accounted as n2 equals maybe 3 and n1 equals 1, and this can be called as L alpha. So in this way, okay. If so, I want to say it for the last time when we have our value of lambda near to the origin, that means it has larger frequency and it has a huge amount of energy. And due to the huge amount of energy, it would target the inner shell electrons. And because of that, high energy characteristic X-rays would be formed. Similarly, if we further increase the lambda, that means continuous decrease in frequency. Continuous decrease in frequency means continuous decrease in energy. And when the energy decreases, the X-rays now don't have that much of energy to knock electron from the innermost shell, but so that's why it would target the outermost shell electrons. And when those electrons are knocked off, we get spectrums, and these are just the so these are just the notations, uh, how we show those transitions. Okay, thank you so much for watching this. I hope you you understood this chapter. I tried my best. Now I think I should make another video uh, on diffraction of X-rays and Compton scattering. Okay, so now these topics are quite important, so I think they deserve a standalone video. So thank you so much. This is the end of this video.